gradient function, you are now going to have a basis of the gradient of a tangent. It can be that you will have a tangent over here or a tangent over there in tangent. Clear? So, if you're now going to get the gradient function and equate it to 0, if this is now going to be equal to 0, then that means you have a horizontal line. Correct? Clear? You will have a horizontal line if you have the gradient function equal to 0. So, all you need to do, if you have an increasing or decreasing function, decreasing function, this one, y prime, or your first derivative must not be equal to 0. Okay, so that's the first thing that you need to know. But then, that means if y prime is not equal to 0, it's either the gradient is like this, curves to our, okay, if it is not equal to 0 there, it must not be equal to 0, right? So the gradient function m must not be equal to 0 because what we want is to have an increasing function or a decreasing function. So here, what is now the gradient here? The gradient here is going that way. So what? The gradient here, m is, it's going from left to right. So m here is positive. M here is positive, m is negative, right? Can you follow?
Yes,
M
teacher.
is negative. So the symbol of the gradient is actually going to tell us if it is an increasing or decreasing function. Okay? It will tell us if it is an increasing or decreasing function. So what you need to do is if, okay, if y prime is greater than 0, meaning it's positive. If y prime is positive for values of x0 to x first value from your test of x1 to x2, then you have an increasing function. Okay? If however, if y prime is lesser than 0 from a range of values from x1 to x2, then you will now have a decreasing function. Okay, so the idea here is if you have your Cartesian plane, let's say we have the Cartesian plane like this. This is now the x, that is now the y. To know at a particular spot of the graph, to know if it is increasing or decreasing, you just substitute values in x, meaning maybe from 0, x0 to x1. Okay? And then you test this one out. You see if it is okay. If it will provide you when value of here is positive and value of here is still positive, then that means now that at this interval, it is now increasing. Same is true if you, let's say this is now 7 and then this is 8, for example. If you're now going to test that and the value is decreasing or lesser than 0, then at that particular interval, it is now going to be a decreasing function. Why it is now decreasing? Okay, are we clear on this? Yes or no?
Yes, teacher.
Okay, so let's solve some examples. Let's try to solve some examples here. Okay, without graphing, try to determine if we have, let's say, the function f of x is equal to x cubed minus 3x squared minus 9x plus 11. Mm, okay, find the behavior of the function from x greater than what's this? From a range or from 0 until 2. Okay. At that particular spot, without graphing, will the graph be increasing or decreasing? So with this, you need to do what? You need to do your first derivative test. Okay? First derivative test. So what we need to find is your f prime of x. So you have here f of x is equal to x cubed minus 3x squared minus 9x plus 11. You will now get what?
3x squared minus 6x minus 9.
Minus 9. And then we need to test this one. We need to test at this interval.
Yeah.
This interval. So from x lesser than 2. Okay. So you can use x1, okay, here. And then you're now going to compare it when the value is x2, okay, positive 2. If the change, if it is now going to give us a negative or a decreasing value, then that means it is a decreasing. Okay, if the value is decreasing, remember, as we go higher in x and the value is becoming lower, then that's decreasing. If you go higher in x, but then the value of the function increasing, the behavior of the graph is increasing. So let's substitute. So we have here 3x squared minus 9 when we have, let's say, greater than x. So 0 0.1, 0 0.5, or okay, something like that. So even if we plot 0 over here, okay, when x is equal to 0, what is now the function? We just need a base value, x equal to 0. When x is equal to 0, f prime of x, we will now get negative 9. Okay, that's the base value, correct? When x is 2, comparing it to 3x squared minus 6x minus 9, so take note, yeah? So when we have here, when x is equal to 0, when x is equal to 0, the gradient is at negative, what's negative 9? Negative 9 per 1. Okay, let's just, I think it's not possible to plot or to graph. Okay, so let's just compare it to the second value. F prime of x when this x is now equal to 2. Okay, so second value is what?
Mm,
What will we get? That is now 4 times.
negative 9 as well. Negative 9.
When x is
Yeah. Then 12 minus 12. 0 minus 9.
12 minus 12, 0 minus 9. Why? Negative, there's no change. What's happening? Cannot. There should be a change there. That means they have the same gradient. Negative 9 per 1. Wait, let me read the definition again. First derivative test. Maybe we can have the definition. If, oh, I see. If f prime x is lesser than 0 for the values in the interval, so negative 9 is less than 0, negative 9 is still less than 0, then the function is decreasing. Okay. So I think I interpret if f prime of x is less than 0 for all values of the interval, okay, if f prime x is lesser than 0 for all values of the interval, then it is decreasing. Okay, so less than 0. Yes, right? When we have here 0, when x is equal to 0, it will produce negative 9. So less than 0. When we substituted 2, which is now the higher limit, okay, of our interval, it is still going to give us less than 0. Okay, clear? So that means if it's less than 0 here, it's less than 0 there, then it is now a decreasing. The behavior of the graph from 0 to 2 is decreasing. Okay, we can test with 1. because 1 is found here, right? Let's test as well in 1. I'm just curious. If we have here 3x squared minus 6x minus 9 and x is equal to 1, what will be the value of this? What is now f prime of it?
Negative 12.
Negative 12. So that means it is still negative, as you can see. So it's safe to say now that from the interval of x0 to x2, the graph is going down. Clear?
Yes, teacher.
Okay. So this is now your what's this? This is now your first derivative test. So the next lesson that we're going to have is called your stationary points. Okay, stationary points. Stationary points are found in a graph. Okay, so these are now the points. These are the points in the graph of the function where the gradient is 0. Okay, so that is now considered as a stationary point. Okay, this is now, there are two types of your stationary point. Number one, the first type of stationary point is called your uh, mm, wait, I forgot. Wait.
Maxima.
No, yes, that's an example. Maxima and minima is an example, but we call that one point of another term for vertex. Point of
Curvature.
turning point. Oh, okay, sorry.
Huh.
Turning point. It's either a turning point, or number two, we have a point of inflection. Okay, so a turning point, this one is, we already discussed this when we were in the lower level. A turning point is we have two types of turning points. So we have seen it in quadratics and cubics. So if you have a parabola, you do like this. At this point, at that vertex over here, this is called a turning point, wherein the graph goes up and then turns and moves to another direction. Okay? So a turning point can be of two types. It can be a maxima or minima. Okay, maxima or minima. Now, it doesn't stop there. We can further define it that for a maxima, this is now a change from a point where the graph, the behavior of the graph from increasing to what? to
To decreasing.
decreasing. Yeah, maxima. It is a point in the graph where the behavior changes from increasing to decreasing. Okay, while a minima mini mini where the behavior minima, it's going down, so that is now decreasing to suddenly curves up to increasing. So that's easy to understand. Maxima and minima is easy to understand. However, we are the stationary points are not only made up of your turning points. We also have what we call a point of inflection. So what is a point of inflection? A point of inflection is neither it will still give you a gradient of zero. However, it doesn't give you, it's not a maxima or a minima. Okay, so that's the easiest way to understand it. It is a stationary point that will give you a gradient of zero, but it's not a turning point. So it is not a turning point. Okay, so it will be easier to understand if I'm just going to make a graph out of it. Okay, so let's take a cubic function for now. There are many graphs of a cubic function. One particular graph of a cubic function is something like this, right? Wherein something like this is, we can easily distinguish a maxima and a minima, right? This is now x cubed. So over here. And if you're now going, this point over here will also have a gradient of zero. And this is going to become your minima. Okay. However, there's another graph of your cubic function wherein it doesn't have a maxima or minima. Okay. The graph is going to be like this. You have seen it before when we were using Desmos. Okay, it goes like this, and like this. Right? The curve here and here is cut like this. It goes like this, and then suddenly goes like this. Okay, if we are now going to trace the gradient, the movement of the gradient here, okay, there is the gradient from the outside. That's the gradient from the outside, gradient from the outside, gradient, as you can see, it's becoming shallow, correct? And at this point, it will zero gradient, okay? A zero gradient, and then suddenly shifts, wherein the gradient now is on the other side. Do you understand what I'm trying to say here?
Yes,
There
yes,
is
sir.
a shift. Okay, there's a shift from the outside to the inside. Okay, I'm going to exaggerate it. Okay, I'm going to exaggerate it so that you can see. So remember your container, remember your container, how does the graph look like again? How does the graph look like?
Uh,
It's going to be fast to slow, right?
Fast to slow.
It's fast to slow and then slow to fast. But it is
Mm.
a continuous, it's a continuous motion. Okay? Fast to slow because of that curve, and then slow to fast. If you're now going to determine the gradient of the tangent over here, if you're going to draw a tangent, you can see that it will be fast. And then somewhere here is going to be slow. Correct? Yes? And then somewhere here it's a very, very slow. There will be a point wherein it will shift or change. Okay? This shifting point, okay, at that particular point, it's now going to shift from the left side, from drawing the tangents on the left side, the tangents now becomes from the right side. Okay? You get the idea of it? So there will be a shift. So when will this shift happen? Okay? From the left side to the right side. When will that shift happen? That is now called your point of inflection or inflection point. Okay? Okay. So that is now your point of inflection. It's a shift. Okay? And this one can be seen in many graphs. It is now going, it is not a maxima or minima, but the behavior is not changing. Okay? Here in this point of inflection, it gives you what? What behavior can you see there?
Increasing.
It marks, okay, its behavior of the graph. Okay, point of inflection marks the point where is a shift in the graph, but the behavior remains the same. Meaning, from it can be from increasing after the inflection, it is still increasing, okay? Or originally in the left, it is now decreasing, and then after the inflection, it is still decreasing, okay? It is possible that way. So it is what? Yeah, the shift that you are is fast to slow to slow to slow to slow, and then you are expecting it to become zero, right? From fast to slow to slow to slow, and then suddenly it shifts, it changed behavior, slow to fast to fast to fast to fast. And it is still showing you that there is an increasing function. Okay, so that is it. So we will now be using this 3 points. Okay, or your stationary higher order polynomials. Okay, without using Desmos or any graphing calculators. Okay, so these are additional points that we need to find in order for us to be able to draw the graph of certain polynomials. So for example, before I let you go for a break, so if we have something like this, okay, if you have the graph like this, what are the parts that you can see? How many turning points do we have?
2.
There will be 2 turning points. Here, one maxima, one minima. And then, what else? We can check the behavior of the graph here, but what we will get there is points of inflection. Okay? So I'm going to mark this one as one inflection. It's going fast, slowly. It's decreasing very, very fast, and then suddenly decreasing very, very slow. And then from that movement, slow, it suddenly becomes fast again. Okay, so these two are now your inflection. This is now your maxima. This is now your minima. Okay, and together with your x-intercepts, with your y-intercept, it is now actually going to draw a pretty good graph. Understand? So these are now the things that we need next meeting. You know how to determine your inflections, you know how to determine your turning points, and you know how to determine your intercepts with your x and y intercepts. Then that's it. That's your graph. Okay. So that is it for today. Goodbye, everyone.
Goodbye.
Thank you, teacher.